Okay, so I just had some of my minerals analyzed in an electron microscope by means of energy dispersive X-ray spectroscopy. I actually wanted to draw this on the fly as I was talking and explaining stuff to you, but I found out I can't really multitask, so I can't really talk while drawing. And also my motor skills are pretty horrible, so it all looked like the drawings of 3 years old and you couldn't make out anything. So I actually had to do this in advance. Sorry about that. So anyway, about electron microscopy. You know that with light you've got these different wavelengths that make up the different colors of light, not just red as with my pen here, but like the different colors which you can see in the prisma or just rainbow. If you've got just a single wavelength and all the crests and throws or whatever those are called in English at the same spot, that will be a laser. You probably already knew this. And we need sort of the same thing for the electron beam in the electron microscope. We need a monochromatic electron beam that has just the same energy of electrons, so like about 20 kilovolts or something. And that's what happens within the electron microscope. So you've got that monochromatic beam of electrons coming in to the sample and interacting with it. So as I said, stuff happens with the electrons. Those are atoms in the material that we want to analyze, and the electron may just get scattered a bit without any actual transfer of energy to the atoms. That is elastic scattering, or it might even be backscattered to where it came from, sort of. But that's not really important for the analysis. And also inelastic scattering may occur. That may be, for example, secondary electrons, when the electron from our beam hits an electron in the outer shell, in the valence shell, and the electron gets knocked out, but this isn't important for analysis either. And we actually may get Bremsstrahlung, where the electron from our electron beam loses energy, and that energy, as energy is never lost, it just gets transferred to something else, actually becomes an X-ray, a Bremsstrahlung X-ray. You can actually look for my videos about Bremsstrahlung if you just search for this word within my videos. But that is a continuing spectrum, so it may have all different wavelengths, and that is really, really useless. You cannot analyze anything from that, so let's move on. What might also happen is that the electron actually sort of excites the atoms, so they begin to vibrate. And this will actually be, as you probably know, heat. So the electrons may actually heat up the sample, but this is not useful for analysis either. Or if you've got a conductor, a semiconductor, you know that in metals they conduct because they are free electrons, so they're just traveling around in the metal grid here. And an electron from our beam may actually get in there and excite things, so they start to oscillate and induce currents. So that's basically a bit like static electricity. The sample may just be charged up, if you want to put it that way. But this is not useful for analysis either. So let's have a look what is actually a useful interaction for energy dispersive X-ray spectroscopy. That is when the electron from our beam, from our electron beam, moves in here and knocks out an electron from the inner shell of the atom. In this case it will be the K shell, just through one electron into each cell. That's of course not correct, but just for simplification. So let's say that electron gets knocked out because the electron beam has a greater energy than the binding energy of that electron to the actual atom's core, the nucleus. So what has to happen now, that this shell is missing one electron, so that has to be filled up from another shell. And as I said, this is the K shell. Then we have the L shell here, so that electron may jump in there and fill the gap. Or from the N shell, that electron may also fill the gap if it jumps from here to there. That may be K alpha radiation for the first mentioned jump of electrons, or K beta radiation. Of course, this may also happen with other electrons. There may be an L electron getting knocked out and has to be filled up, so that may be L alpha, L beta radiation, stuff like that. But what is also important to note is that you have actually different subshells within these shells. So the electrons will jump in there to fill the gap, And by doing that, that will produce characteristic X-rays. They are called characteristic because the energy level of each electron is very specific for every element, or as some books call it for simplification. The electron shells have a different spacing there, so the way they are apart are very specific for each element. So you can imagine that for each jump from either from an L electron into the K shell or an M electron into the K shell, you get a very specific ray. If it is like, say it would be gold, or it would be uranium, the shells would be, to simplify it, the shells would be further apart or less far apart or something. That is, as I said, very specific for the element. But you don't have just one single energy level, you actually have subshells within those energy levels, within the K shell, within the L shell and stuff. You actually have subshells. So the one important thing to note about that is that you don't get one single monochromatic beam like the K alpha peak like this, but you'll actually get a slightly diffuse beam. So it will look like this, and that will tell you, oh yeah, that in the middle here, as you can see, I can't draw. That's why I did all that stuff in advance. So I try to do it like this. You'll actually have that will be the typical K alpha peak as expected. Well, you'll have a bit around it as well, but this will actually tell you that it's likely that it is like element X. But the thing is that you actually have to compare all the peaks, K alpha, L, K beta, L alpha, L beta and stuff, because actually, say the K alpha peak of one element may be equal to the L beta peak of another element. So it's very important that you look at all those peaks you get in sample analyzation, which may look like this. That will be just a continuous spectrum of Bremsstrahlung and stuff, which I told you before. Then you may have peaks like this, and like this. You may have another peak here, and another peak here, and you just have to find out what kind of elements could be responsible for those peaks. If there are multiple elements, or if these are peaks from the same element. Let's just have a look at that. So let's take a look at this. What you can see here is a graph that was done by a professional. The graph itself was done by the electron microscope, of course, but the labeling was done by a professional. There are tables for the specific peaks of the different elements, but I think it would have taken me 20 hours just to analyze one single probe or something. So anyway, what you can see here is this major peak there on the left side, sort of to the middle. That is from bismuth, as you can see. You can see the different peaks there. You can see it's just each element is labeled with a different color. So for bismuth, you've got those like bright blue peaks here, and you can see there are multiple peaks all over, which could be accounted for that element, but bismuth is quite clear here. And just to the left of that, the other big peak is from silicon. You can see that's quite a big peak as well. And we've got on the right in dark purple color uranium, and we also got aluminum, magnesium, oxygen, and some carbon. Oh, it is important to know, by the way, that any elements that are below carbon in the periodic table cannot be analyzed with this method. Same as if an element is present with less than 0.2% in total weight. So yeah, this mineral sample contains bismuth and uranium and silicon and a few others, as we just saw. So let's have a look at the next sample, which is gumite. Gumite is a mixture of all kinds of different elements, which we can see now. You can see the major peak there with uranium. By the way, if you look at my videos and search for gumite, you can also see how active this is. And yeah, as you can see here, we have a big peak that is very clear for a lot of uranium in that mineral. But to my surprise, we also found arsenic there in the middle on the right, next to lead. And yeah, as you can see, we have a crazy mixture of all kinds of elements in there. Phosphorus and magnesium and barium and copper, and just a crazy mixture of all kinds of elements. I really love this. Look at all those peaks. That's really almost impossible to analyze because there are so many peaks from all those different elements in there. But it's a very good example of chaos. I love chaos. Now the next graph will be quite the opposite of that. You can see just one very well-defined peak from arsenic and from oxygen. That was to be expected because it was actually a sample of genuine arsenic. Arsenic occurs pure in mineral form sometimes, in this case it does. And it is covered with a layer of oxygen, which is very typical. You know that gray layer on lead, for example. If you scrape that off, you have a shiny silvery metal, and it's the same with arsenic. So we just get those nice peaks from arsenic and oxygen. Very clear and easy to see. That is what the actual mineral looks like. Arsenic with that grayish layer of oxygen. Well, now for something very special. What you can see here is obviously calcium fluoride with a large, incredibly large peak at calcium and clear fluoride peak to the left of it. But you can also see a little bump in the middle, right, between calcium and fluoride. That is quite a bit weird. It is not marked to be an element, but it's clearly a peak, so what is that? That is a so-called escape peak. This is actually an interaction within the silicon detector. You know, there's of course something that detects those X-rays, those characteristic X-rays, and all the others that are produced within the sample. And the peak you can see here is the K-alpha peak of silicon, actually. So it's actually the silicon atoms getting ionized by the X-ray that hits them. And as we discussed before, there may be auger electrons in the process of filling up the empty shells. And when that happens, those auger electrons may actually escape the detector, leading to those very specific escape peaks. But how do you know it's an escape peak? Well, the thing is that this escape peak has the actual energy of the parent, like the calcium, minus the energy of the actual silicon K-alpha photon. So that's what determines this as an escape peak. Quite a fascinating phenomenon, I believe. And while that always happens to some extent, you can only see it in very few minerals because, like, the magnitude of that escape peak is also dependent on the actual composition of the materials. So this is a very rare sight to be actually able to see this clearly. I also had some of my nice green fluorescent uranium minerals analyzed. And what you can see here in the middle to the right is a peak of barium. So, well, it was sort of unclear whether I had autunite or uranosursite before. This clearly tells that I actually found uranosursite. As a reminder, here's a photo of the minerals I found under UV light, so you can see the fluorescence. And I actually got a picture that was taken under the electron microscope as well, as you can see here. You may not have said this is not a very high resolution for an electron microscope. That is because when you actually want to perform RDX, energy dispersive X-ray spectroscopy, you have to have the electron beam far away from the source. So this image is just a low-quality byproduct of the actual energy dispersive X-ray analysis, and it's not as good as it could be if the sample had been coated with gold and stuff. So this is just a byproduct. But it's still nice, and you can see the mineral structure quite nicely, especially on the bottom right there. And this is a spectrum from a nice tiny little sample of thorianite, thorium ore, which looks like this in macroscopic view photographed, and like this under the electron microscope. Next will be primary uranium ore, which is actually quite impure, as you can see, a large peak from calcium and lots of other peaks there on the left as well, and silicon, all that kind of stuff. And you probably know how uranium ore often occurs in these little bubbles. And what is kind of funny is that you can actually see this under the electron microscope as well, even though you could not see it from the outside in that sample. So here you can see the uranium ore under the electron microscope. You can see the magnification is not all that high, but it's still quite a nice view on that mineral sample. I didn't know it would show those little bubbly appearance even in microscopic view. And now for something completely different. Silicon carbide, which is really smooth and has a little hair on the left, as you can see. If you want to have a closer look at all the graphs and images, I uploaded them to my Flickr photo stream. The link to my Flickr photo stream is on my YouTube channel page, but you can also go to the set directly by typing in the URL shown here.